Hello and welcome to Space Talk with the American Astronautical Society. I am Dr. Amir Gohardani, the host of Space Talk and the editor-in-chief of Space Times. And today I have the distinct pleasure of welcoming Dr. Casey I. Honniball, visiting assistant research scientist with NASA Goddard Space Flight Center at the University of Maryland, College Park. The topic of our talk is the moon's most important resource. Welcome to the session, Dr. Honniball.
Hi, great, thank you.
Wonderful to have you here. This topic seems a little bit mysterious to me, the moon's most important resource. And I'm very happy that you will shed additional light on this as we move forward. Before that, however, could you tell us a little bit about your educational background?
Absolutely. So I started my educational background at the University of Hawaii on Oahu. I spent 2 years there studying physics and decided that that was really not for me. And that's when I switched to the University of Arizona to study astronomy, to really get into studying the stars and looking at the night sky, because that's really where my passion was. So at the University of Arizona, I got my bachelor's of science in astronomy. And I really I started working with a radio instrument laboratory, and they helped build my instrumentation work. And I was working on radio telescope instrumentation, cameras that would be deployed to many different telescopes around the world, including Chile and Antarctica. And so I ended up going down to Antarctica twice during my undergraduate career. Then after that, I switched back to the University of Hawaii, where I studied geology and geophysics for my master's degree. There, I would build, test, and deploy an instrument that would study volcanic CO2 from the active Halemaumau lava lake that was, while I was there, was active. After I left, it went dormant for a little bit and then came back to life. At the University of Hawaii, I continued after my master's into my PhD, where I studied Earth and planetary science. And for that, I really focused in on looking at the moon and volatiles on the moon, and specifically looking at water and its behavior and hydration in general across the surface of the moon using Earth-based telescopes, including the NASA Infrared Telescope Facility, IRTF, and the NASA Stratospheric Observatory for Infrared Astronomy, SOFIA.
What an amazing journey. And I really love the fact that early in your career, at least your educational career, you really tested one of the subjects and noticed that, well, your passion might lie somewhere else. So this is really a lessons learned for those of you who are listening and those of our audience that actually have second thoughts, and they say, well, do I need to really finish this? I mean, you ended up at NASA anyway, so it's just amazing to see that journey. And I guess the next step in your career became to apply your knowledge. And can you tell us a little bit about that, please?
Yeah, so now I am a visiting assistant research scientist. It's a very long name.
Yes.
And I'm a contractor at the University of Maryland College Park for the NASA Goddard Space Flight Center. And what I do is I basically split my time looking at data that I've collected from the IRTF telescope and SOFIA telescope, characterizing water on the moon, and also developing methods to improve lunar surface science. So going out into the field and testing instruments that astronauts could use while they're out in doing an EVA, or even an instrument that could be rover-based and would be able to act as like a reconnaissance instrument that the astronauts would be able to take the data, look at it, and be able to say, oh, this area here on the moon looks really interesting and we should really go there and sample it. So those are the two areas that I'm really focusing in on right now.
So what is the motivational factor to consider the moon to begin with?
Yeah, so the moon is really It's really an interesting place. I mean, it's the thing that all humans have in common, right? You can look up in the night sky, and every single human on Earth will be able to see it at some point during the night or day. And the moon is really important because it is our stepping stone to get further into our solar system. So it allows us to prove technologies and capabilities before we even try to go to places like Mars, because Mars is really far away. Mars takes, I think it was like 9 months to get there one way. Whereas the moon, it takes us a couple of hours to actually get to the moon and actually be able to start living and working there. So because it's closer, because it's not 9 months away, we can test these capabilities. And if, for God forbid, something went wrong, we would be able to assist the astronauts and potentially bring them home in case anything ever went wrong. So really, the moon is a stepping stone for us to expand into our solar system.
So that would be basically moon before Mars, right? So
Yes.
and you touch upon a very important point, which is that anything related to space exploration, particularly when humans are involved, it's a risky business. It's people's lives on the line, and of course, with our limited knowledge about the universe, it becomes even more riskier because we run into scenarios that we sometimes don't anticipate. So in that regard, what you are doing at this point in time, does that help us with the understanding of both Mars and Moon? Can you shed a little bit more light on that, please?
Yeah, so if you actually go to the next slide, what I'm really doing now is looking at the resources available on the moon. And how that helps us is if we can understand the volatile cycle, which is one of the center valuable lunar science objectives that we have. If we can really understand this lunar volatile cycle, we can understand what kind of volatiles are present. And the most important one is actually water. And if you go to the next slide, water is so important because it's what we need as humans to survive. It can provide drinkable water, breathable oxygen, and rocket fuel. So if we are able to find water on the moon, which is what I'm working to do, and characterize it on the surface of the moon, maybe we can find an area on the moon, like permanently shadowed regions that store a lot of water that we would be able to utilize for these drinkable water, oxygen, or rocket fuel. Now, that allows us to potentially have the ability to have a more sustainable human presence on the surface, as well as refuel so we don't have to bring all of the fuel that we need to go, say, to Mars or to another further away body. So really understanding if there's water available, how much is there, what is its behavior, and is there enough that we can utilize it for a sustainable presence in our solar system?
Very interesting. And we all probably read on efforts to try to detect ice or water on Mars. So similarly, has the perspective always been that water was available on the lunar surface at all times, or has that theory shifted based on recent findings?
That's a great question. So when astronauts went to the moon during the Apollo era, they brought back samples that they really wanted to study to see if they could find any volatiles of any kind, such as water or hydrogen. But when they studied these samples, they really didn't find any water or hydrogen or hydration of any kind. And so for a long time, I think it was about 50 years, we believed that there was no water on the surface of the moon. If you go to the next slide, however, in 2008, we had reports of a reanalysis of really special Apollo samples. These were volcanic glass beads that were returned during the Apollo mission. And what the reanalysis did was use improved technology that could measure abundances of hydrogen down to smaller abundances. Now, what they found is that there's actually small amounts of hydrogen inside these volcanic glass beads. and they found what we know as a diffusion profile. So there's more hydrogen in the center and less at the rim of the bead. And what this told us is that these volcanic glass beads were sourced from the interior of the moon during a volcanic eruption. And that volcanic eruption below the mantle had some type of volatile elements that included hydrogen. Now, whether or not that's water or some other type of volatile is questionable because we can only measure hydrogen in these samples, but that really shifted our understanding of water and hydration on the surface of the moon, because all of a sudden these really special samples have shown that there is hydrogen, there is potential for hydration on the moon. And then in the following year, in 2008, we had 3 spacecraft make unexpected detection of hydration across the surface of the moon. So these plots here are from the Deep Impact spacecraft. And if you look at the plot on the right, we can see that they measured different abundances of hydration across the surface of the moon. Now, this was revolutionary because, when we brought back the Apollo samples, we really didn't find any hydration. But then the year prior, we found hydration in these special volcanic glasses. And then the next year, we find hydration across the surface of the moon. So that was pretty revolutionary for lunar science, because all of a sudden there's water on the surface of the moon. However, if you go to the next slide, what the spacecraft measured was actually what we call a 3-micron band. So 3 microns is just beyond what we can see in the visible spectrum. Now, this 3-micron band is actually a combination of potentially hydroxyl, which is an oxygen and a hydrogen attached together, or molecular water, which is H2O, like we know and love to drink. Now, hydroxyl is really different from molecular water because you don't want to drink it, right? You really want to know if this 3-micron band is due to hydroxyl or water. Now, this 3-micron band was created by the symmetric and asymmetric stretch of the OH bond, which you can see these little molecules here doing. And you can see that all 3 of these do this little dance that they have, which creates this 3-micron band. So when we were looking at this 3-micron band from the spacecraft data, we really had no idea whether or not it was created by hydroxyl alone, molecular water alone, or the combination of hydroxyl and molecular water.
Very interesting. Here, a new method for water detection was discovered. Can you tell us a little bit about that?
Yeah, so during my graduate work at the University of Hawaii, I was working with my advisor, and we're like, we're working on this 3-micron characterization with the IRTF telescope, but why can't we determine whether or not water is really present on the moon? You can't do it at 3 microns, but is there another wavelength that has a water-only spectral feature? Well, it turns out that there is, and it's just slightly longer than the 3-micron band. So we call this the 6-micron molecular water band. And it is due to the water molecule doing this bending mode around the oxygen. And hydroxyl cannot do this motion. And so therefore, there is no contamination from hydroxyl in our 6-micron molecular water band. So what we do then is we use the NASA Stratospheric Observatory for Infrared Astronomy to really look at molecular water on the surface of the moon using the 6-micron band. Now, I use both the IRTF and SOFIA to look at water on the surface of the moon. So with the 3-micron band, I am I am looking at the total hydration on the surface of the moon. With the 6-micron band, I'm determining how much of that total water is actually due to molecular water. And I'm working to characterize the behavior and distribution and abundance across the near side of the moon.
Very interesting. So your initial research pointed to the 3-micron, and then you advanced to the 6-micron because of the challenges of really distinguishing what's happening, right?
Yeah, exactly.
Can you please tell us a little bit more about SOFIA?
Absolutely. So SOFIA is the Stratospheric Observatory for Infrared Astronomy. It flew at 45,000 feet, which is above what commercial airliners fly. And it's basically a flying telescope. as you can see in this model image here of Sophia on the bottom, there is like this cutout where it's open up to the inside of the plane to reveal the telescope inside. Sophia has a really unique instrument called the forecast instrument that allowed us to look at the 6-micron molecular water band on the surface of the moon. And the reason we had to use Sophia is because this 6-micron band is completely drowned out by Earth's atmospheric water on the surface. So we had to get above as much of the atmosphere as possible to be able to distinguish between atmospheric water on the Earth and water on the surface of the moon.
Wonderful. And in 2020, you actually made a significant discovery with Sophia, correct?
Yes. So with Sophia, we actually made the first observations of the moon with Sophia in 2018. And what we found from the 2018 results and reported in 2020 was that we found a really nicely prominent 6-micron spectral feature on the surface. It was about 1 to 2% in strength. And it was the first time that we could be confident that we had detected only molecular water on the surface of the moon. We made these measurements at high southern latitudes near the Clavius crater, which is that little circle on the bottom of the full moon image. And Clavius is actually one of the biggest craters that you can see on the moon with your naked eye, which we thought was pretty neat. And then the image in the background shows where in Clavius we were measuring. And so with these 2020 results, we reported the first detection of molecular water only on the sunlit surface of the moon.
This is really significant, and so much adds so much value to the science involved. Please tell us a little bit about the interaction of the solar wind, hydrogen, and water.
Yeah, so a lot of questions come around like, well, okay, how did water get to the moon? Because when we believe the Earth, or when the moon was formed, we believe it was formed from the giant impact. And we believed that it was such a hot event that all the volatiles should have been lost from the moon. And the way that water could have gotten to the moon is through comets delivered to the moon before the moon created a solid surface. So comets would impact the moon and in place any water or volatiles that they had into the lunar interior. Now, this water could later be erupted onto the surface of the moon during volcanic eruptions into those volcanic glass beads that I talked about before that were special samples brought back by Apollo that were the first indication that there might be water on the surface of the moon. So if you look at that quarter of the moon on the top right, there's some little hot spots in red. That's a volcanic deposit on the moon that we look at to see, is there higher abundances of water that were derived from the lunar interior that could have come from these comets. Now, water can also get to the moon in a more contemporary way. So the sun is constantly releasing hydrogen through its solar wind, and that's constantly bombarding the surface of the moon. So the moon is getting a constant supply of hydrogen to its surface. Now, this hydrogen can interact with lunar surface materials like oxygen and create the hydroxyl. Now, hydroxyl isn't necessarily what we want, right? Because it's the active ingredient of drain cleaner and you don't want to drink that. But what could happen is that at high lunar noon temperatures or during a micrometeorite impact that create really high temperatures, you could take 2 hydroxyl atoms or molecules, combine them and make a molecular water. So I talked a little bit about micrometeorite impacts creating high temperatures on the surface that could take 2 hydroxyls and make molecular water. But micrometeorites also play another important role in the fact that they might have volatiles and molecular water present on them that they could deliver to the moon themselves. So all of these different ways are ways that water could have gotten to the moon.
Wonderful.
When we go to the moon, we need to understand where this water is actually stored. We know how it gets to the moon, but we need to understand its abundances and the location, and if there's any places that we can really concentrate water. So there's three different ways that water can be stored on the surface, and it's in permanently shadowed regions as frost or ice. You see in the background is actually of the south pole of the moon. And those blue splotches that you see and the teal ones are permanently shadowed regions that might be storing a lot of frost and ice that we might be able to extrapolate. However, these areas are really, really hard to go into. They're extremely cold. They never see any sunlight. The depression of the craters on the moon is so deep that the sunlight just can't get in there. And so working in this environment is going to be extremely complicated. We don't know how to survive in a permanently shadowed region on the South Pole just yet. These are things that we need to test. However, if we can find that water is stored at much easier locations, like on sunlit areas of the moon, maybe we can extract water that's actually attached to a lunar grain or inside impact glasses that are formed during the micrometeorite impact that might store volatiles and water. Now, we can also look at those volcanic deposits that I mentioned before with the volcanic glass beads and see if there's enough water concentrated at those locations that we might be able to extract and utilize. So understanding the abundance, the behavior, and the location and concentration of water is really what my research is all about.
That's a great research topic, and I believe it's so impactful because it really impacts the way we think about life beyond Earth, right? Because usually we associate water with life and some form of life, and it's a very interesting research topic that you're involved in, and certainly because of better instruments, we have probably a higher chance of trying to detect these secrets as we go along, right?
Yes, absolutely. With more advancing technology, the more we'll be able to really understand the water cycle on the surface.
Excellent. This has been really interesting to me, and I like to learn more about the life of a research scientist. You have partially shed light on this topic and your particular journey, but we have a wonderful collage here that I ask you to please walk us through and highlight some of the elements that's been part of your exploratory journey.
Yeah, absolutely. So I'm actually going to start a little bit at the beginning of my lifetime before any of these pictures were taken. In the first grade, I was actually diagnosed with dyslexia and held back and repeated the first grade. Since then, I had, assistants in school. I had tutors all throughout my schooling until I was a junior in high school. And my parents actually thought I was going to run away and join the circus. That was pretty, I proved them wrong, I think, a couple times. So while I was in high school, my junior year, when I no longer had assistants in school with homework and tests and everything because of my dyslexia, it was really when I started to be like, okay, what am I going to do with my life? I want to be able to travel. I want to experience things that no one else is getting to experience, right? I think like all young kids want that kind of thing. And I had an inkling that I wanted to be an astronaut. So I really enjoyed astronomy. That's when I decided that I was going to go to the University of Hawaii to study physics, because I really enjoyed my physics class in high school. As we know, that didn't turn out very well for me. I didn't like physics at all in high school, and I ended up switching to astronomy, which I highly enjoyed. And that's really when a lot of doors opened up for me, because I found something that I was passionate about. I really enjoyed working with instruments and building them and testing them. And I really enjoyed going to a telescope and observing the night sky. I started out with radio telescopes looking at molecular clouds. That allowed me to go to Antarctica. So if you look there's a picture in here of me walking in the snow with a colleague. It's kind of in the center. Yep, that one. That's us in Antarctica at the Large Balloon Telescope launch facility, launch pad. And, our footprints are the only ones there. It was amazing. And then there's a picture of me next to the McMurdo station sign on the right-hand side in the big red jacket that they give you to go down to Antarctica. And then, I got to deploy high altitude balloon telescopes that were looking and studying the stellar life cycle in the molecular clouds. I got to deploy cameras to Chile. That was really interesting. And then when I went to my graduate career, that's when I really started to focus in on my research. I built and tested an instrument that I would deploy to the lava lake. If you look on the top two center images are of me and the instrument that I built at the Halemaumau lava lake. And you can see that there's some active lava in the background there that we're looking at. We're trying to study the CO2 emissions coming from that lava lake. If you go down from the one all the way on the bottom, that one is actually an image that the camera took of the lava lake that came from the instrument that I built. That was really neat and exciting. We got to, if you go to visit Hawaii and you go to the Halemaumau lava lake, you can go and see it. But we get to go up close and stand on the edge of it because we're doing science and conducting science. And this is something that I really wanted to be able to do, go places that a lot of people don't get to go. And this allowed me to do that. I found a passion and I let it drive my direction. And that's also where I met my graduate advisor, Paul Lucy. And he really helped me focus in on studying the moon, because what I found is that when I was studying the molecular clouds and stellar formation, it was just a little too far out of reach. I wanted something that was tangible to go to in some time in my lifetime. The moon, obviously, is close enough to go to. He was super interested in studying the lunar surface and water. And so we ended up, looking at using the IRTF and looking at SOFIA. And so some of these pictures in here are of him and I working together, studying the moon, looking at data, being on SOFIA. The center image above one of the center images is me and Paul. That one right there is me and Paul working together. The one right next to it on the right is me and Paul taking the picture of me on SOFIA when we made the first observations of molecular water on the sunlit surface of the moon. That was an exciting time. And then, these experiences throughout my graduate and undergraduate careers allowed me to have other experiences that weren't related to my research. So, I went on internships that I studied different things, where if you go to the bottom left picture, that's me and a bunch of our interns from the Lunar and Planetary Institute graduate summer in the graduate from Lunar and Planetary Institute. We are actually in the Johnson Space Center sample curation room. So we're wearing the bunny suits because, you don't want to contaminate anything. And, part of that allowed me to go to the neutral buoyancy laboratory. So on the right-hand side, there's a picture of me standing next to an astronaut who's about to do some training in the neutral buoyancy lab. So all of these experiences were really great. And I wholeheartedly believe that they came to me through finding something that I was passionate about and pursuing that passion to its fullest extent.
Yeah, for sure. I think you have explored very new areas and left your footmarks already, as literally here in the snow and really in science. And I think it's a very important lessons learned for particularly young individuals who are interested to pursue their passions and not necessarily a topic, because as part of this series, we always would like to hear the career tips that the experts sharing with us. And I think if we can summarize in some form, some of your recommendations is really to follow your passion, because you're a living example for how wonderful that journey has been. And you're still excited about these topics, and you actually discover new areas of interest. And it's really fascinating to see that, particularly being an experimental aerodynamicist back in the day. I really love the instruments and working with them and really understanding what the physical world is like. And this is very similar to what you've done here. So I was really amazed to hear that you actually built this instrument, and this is the result. And it's really amazing. I can imagine the satisfactory elements it will give you. So, and with that, I just want to maybe end on this note of asking you, if you were summarize anything that your career has taught you so far, and of course you have long ways to go, you've come very, very far, with others, what would that be?
If I were to summarize, I think the main thing is find something that you're passionate about, but also don't let it constrain you. Because I've found so many different things by exploring different areas of my passion, right? Taking my passion and letting it go in different directions. I think that is super important, because you'll find that you have passions outside of what you thought might be your passion, right? I thought it was physics. I let that expand a little bit, and I discovered, no, it's not physics, but it's astronomy. And then, the travel aspect was great. And I think one other thing that I would really like to say is, your work-life balance is also extremely important. If you don't have a good work-life balance, you can burn out. I mean, that happens all the time. So making sure that you're focused on your passion, but also focused on being as the best you that you can be as well.
That's a great piece of advice, which applies to virtually almost anybody who works, right? So we need to find that balance at all times. This has been really, really interesting, Dr. Honniball. Thank you for so much for sharing your expertise and your knowledge and your valuable time with us here at Space Talk. And you're an exemplary role model for many people who, since you have overcome so many challenges and you have achieved so much, and it's just amazing to witness that and hear your story about how you got this far. So thank you very much, and it's been a pleasure to have you here at Space Talk.
Thank you so much for having me. It's been awesome.